Hi. So as Tom was saying, I'm going to talk today about some work that I've been doing, which is optimization algorithms large. This is kind of the intro talk to another talk, which will happen right after it by Elliot. So I also, this work, I started while I was at Google Brain, the first time when I walked in. So it was with Fabian and Bart, and then Elliot joined, who's a random matrix theory person. And then the pandemic hit, and Elliot and I were stuck in an apartment together for 2 years, and it started to blossom, this research. So we've been doing more and more work in this area. Okay. The other thing I want to point out, by the way, I am neither a random matrix theory person, nor am I a numerical linear algebra person. I am an optimization. Okay, so if anything you get out of this talk is about optimization, that's great. Okay. Oops, is it working? I click it. All right. So this probably won't offend anyone here because you're not optimization, but I'm going to start off with sort of talking about some critiques in the optimization community that I say are kind of interesting for us to look at. The first is this idea of theory versus practice. Okay, so what happens a lot in optimization is the optimizers will prove some sort of bound. Okay, then you create this great algorithm, then you give it to people to actually work with, and it does absolutely nothing like what the theory actually would suggest. Like the theory is not even on the same order of magnitude, okay? Or they just ignore whatever you say from the theoretician because it doesn't work in practice. So this is sort of what you tend to see. So these are runs of some algorithms. Those are the gray lines here, okay? You see all these gray lines are down below, and what the bound is up above. And this is actually quite generous in terms of a bound here. This is, most of the time this we're seeing it's like not even on the same page. Like you don't even put it on there because it wouldn't even be on the same order of magnitude, okay? And this kind of goes along with this idea of theory versus practice, which is that there's sort of this mismatch of assumptions that we have. So what tends to happen in optimization theory is that you tend to want to put very, very general assumptions on your functions. Okay? And the assumptions don't really match what the actual practitioners are actually using. So they're not what they're actually running these algorithms on. And there's a third thing which I missed here. And the third thing is that the complexity now isn't the only thing that matters in optimization. It's not just producing an algorithm that converges the fastest. That's not the issue anymore. What they tend to do now is, right, you solve your optimization problem, but you're going to take whatever you get from your optimization and you're going to do something else with it. Okay, you're either going to do some sort of statistics on it, you're going to apply it to some other thing, okay? But the actual problem that you're solving in optimization isn't actually the one that you want to solve. Okay, so there's this mismatch of sort of the idea of complexity. Okay, so the next talk and this talk a little bit is going to focus on this theory versus practice and sort of what are some good assumptions to put on our algorithms. So what do I mean by this theory meets practice? So this talk, and what I hope you can want to get out of it, is that what we're looking for is actually that this is exactly what happens in practice. Oh, all good? Okay. Okay, so what am I doing here? So as you want to put out here, we're running a stochastic algorithm on a real data set. So here, this is the CFAR10 data set. The CFAR10 is an image data set. Okay, it has pictures of cars and planes and cats and dogs. If you've never seen this before, here's some examples of it. This is questionable if it's a car, but let's assume it is. Okay, and this is a real data set out there. What I'm going to run on here is basically like a least squares problem. So I'm going to take my CFAR data set, which is images. I'm going to think of each image as a row. Okay, I'm going to multiply it by a random matrix, and then I'm going to take an activation function, a pointwise function on each of the entries and apply it, and that becomes my A. And then I'm going to run a least squares. So I'm just going to minimize norm of AX minus B. Okay. And the idea is the algorithm that you tend to run on these large problems are the SGD algorithm, which is just stochastic. So here I'm just running one run, and you see it's like very, very squiggly. Okay. And what my goal is that I want to actually exactly predict the behavior of this random algorithm. Okay. I want to actually be able to tell you at each iteration of the algorithm exactly what the value of SGD should look like. Okay. And so that's what I'm doing with this curve here. That's not the mean of anything. That's not the mean of the runs. That's I predicted ahead of time what SGD would do, what the stochastic algorithm. How do you do that? Well, you of course need some inputs here. So what I'm running for my inputs is I'm going to assume that I have available the eigenvalues of the matrix A transpose A. Okay, so A transpose A, and also the target vector B. Okay, but the goal of this is that you can actually just predict the behavior from the eigenvalues. That's all you need. You don't have to worry about the randomness anymore. Okay? That's the goal. Okay. So what do typical machine learning problems look like? Well, if you ask an optimizer, they would just say the following. The whole idea of machine learning is that you're minimizing some very large finite sum. That's it. Okay. Now, what is this finite sum? Well, you can imagine that each of these f sub i's, this I corresponds to the loss on a single data point. So you're taking here an average of the losses of every data point. Okay. And the goal of optimization in general is to produce some sort of iterate xk, which is nearly optimal for this problem. So that could mean many different things. That could mean that the gradient is small. That could mean that the function values are close to the optimum, or you could have a distance to optimality. Okay. Now, the other thing that I'm going to say, which is typical in machine learning problems, is that they're going to be what I'm going to call high dimensional. So this means that not only do we have a large number of samples, so we have a big data set that's corresponding to the I, the number, this n here, but also we have a lot of number of features. D. So the space for which we're minimizing over is also big. Okay, so both N and D are large. I'm going to use features here, by the way, because this is the statistics, and machine learning is usually in statistics notation. But so that's what the features represent. They're the space for which you're sort of minimizing over. And just to give you a little bit of perspective of what we're talking about now, the state of the art for many ML models have millions and billions of parameters. Okay, so here are some examples. They're in the billions here. The latest Google language model is like 500 billion parameters. Okay, that's the D size that we're talking about. So that's the scale we're talking about. Now, the other thing which maybe you're not so familiar with, and which Jeffrey will be talking about probably in more detail later on, is that in reality, the actual number of features, ratio of features to samples is actually pretty constant. So what do I mean by that? Is that if you actually look at state-of-the-art models over time and plot their training data set size, so the N versus their parameter count, and you plot it, sorry, this is a little dark, but you can see that it follows sort of a straight line. So the number of parameters and number of samples are actually kind of proportional to each other. Why am I making a big deal about this? I'm making a deal about this because this tells you that you're not necessarily in the classical statistical setting. So the classical statistical setting would say that I fix my D and I think of N, number of samples, extremely large. That's not actually what is being run in terms of state-of-the-art models. Okay, now, of course, you could achieve the same performance level using things which have N much bigger than D, okay? But these have been sort of optimized for other things beyond just that, and they tend to have a proportionality constraint, okay? So Jeffrey will talk about it, and I actually stole this from Jeffrey's talk, so he'll actually have the same picture in it. Again, I said I was the intro person, advertisement for a bunch of other talks today. Okay, so what makes sort of high dimensions very different, and probably for this audience, everyone knows this? Well, the simplest answer is that you have more room, so you have more possibilities. So inputs which generate sort of your worst case complexity can be really, really far from the typical one. And so how do you actually capture high dimensions? Well, what you typically do is you put some sort of probability distribution on your inputs. Now, as just a remark, we'll actually show things which have deterministic designs, but a way of sort of getting those deterministic designs is you put probability distributions on the inputs into your algorithm. Okay, and there's a bunch of work on this. Tom has done a bunch with Percy Dive. I think a bunch of people will be talking about this type of thing later on. Okay, so let's take the simplest optimization algorithm, convex problem out there. And if you ask anyone, it would be a least squares problem. So all you're trying to do is you're trying to minimize the norm of ax minus b squared. So here I'm thinking of my matrix A as my data, and B as my target. Okay, so what I mean by putting a random input is that I'm going to assume that my data matrix A is random, so that it's n by d. And I have a random target vector B. And also you can think of having a random initialization. You don't need to. Okay. And things that you're interested in optimization are often quantities like, well, when is the gradient small? So let's call this the halting time. So this is the first time that the gradient falls below some epsilon. And let's just look at what happens if we run the standard gradient descent algorithm off of it. So that's just all I'm going to do is I'm going to move in direction of negative the gradient by some amount proportional to the size of the largest eigenvalue. So what do? What happens as you make dimension bigger? So as you see for large models where both D and N are both large, and I'm going to assume that they're proportional to each other. Okay. What you see is that the halting time will always converge to some point mass. And it seems to be independent of sort of the distribution that you put on the A's and B's. You can see this in a picture here. So what I'm plotting here is the model size, so the D parameter. And here I'm plotting the halting time. So what we did is for each D, we generated a random matrix, we generated a target vector B, we ran the gradient descent algorithm off of it, we computed the first time that it's less than epsilon, the gradient is less than epsilon, and we plotted it. Okay, and what you're seeing in the shaded regions here are the variances of the halting time. So as you can see, as I make my model size get bigger, the variance across these things is converging to some fixed value. The different colors represent different generations of the data. So here I'm generating with Gaussian, which is the blue, Bernoulli, and student T. So why do we see this? Okay, so we see this because for deterministic first order methods on the least squares problem, we have this relationship, which is that for every first order method, there's a polynomial in the Hessian that appears. So we can relate every first order method to a polynomial in A transpose A. So here I'm minimizing this. Here for convenience, I'm just going to assume that I have a generative model just for illustration. You don't need this, but you'll have that B is some A times some unknown signal X plus some noise. Okay. By first order methods, if you've never seen this before, a first order method is just a method which produces an iter xk, which is in the span of the previous gradients. Okay, so this includes CG. Okay, what it doesn't include is it doesn't include Newton's methods. It doesn't include quasi-Newton's method because the matrix can actually change the span here if you go along. But it includes gradient descent. So what do I mean by this polynomial in the Hessian? Well, let's just take the easiest example, which is gradient descent. Okay, so if I take gradient descent, it's just xk, which is xk minus 1 minus the gradient. Oops, I missed a gradient. Sorry, there's a gradient L there. All right, if I plug in what the gradient of L is, well, it involves A transpose A, so it involves this Hessian H appearing. Okay, and so I can factor it out as I minus H times the previous gradient plus a noise term. And well, xk minus 1 is just the same as xk, so I can replace that again. And I can iterate all the way down until I get down to the initialization. Okay, so I get I minus h to the k times the initialization plus some noise. So by this polynomial in h, what I mean is this function here. And if you do a worst case complexity analysis, say you want to find where the norm, the distance to optimality is less than epsilon, what you'll see is that it will take kappa, or the condition number, times log of 1 over epsilon number of iterations. So the condition number here is the largest eigenvalue of the Hessian over the smallest eigenvalue. Now, it turns out every first order method has this. So let's take another example of a first order method. This is called momentum. Okay, so the basic idea with momentum was that, well, instead of just moving in direction of the negative of the gradient, which is sort of current information, what you do is you say, well, maybe I should remember where I came from. Like, I shouldn't just use my current information. I should remember some of my past of what I was doing. And so that's incorporated into this YK. And then what you do is to choose your next point, you choose it by choosing a linear combination of how much of the past you want to consider versus how much of the current point that you want. Okay, so this delta here is going to represent how much momentum, the past, so that's where the momentum idea comes from. And this gamma is your step size, is going to control how much of the gradient. And what you can show is that for very specific choices of your momentum and your step size, that if you want to make, in worst case complexity, the distance to optimality small, it requires root kappa log 1 over epsilon number of iterations. Okay. What do these momentum and step size parameters depend on? They depend on both the largest eigenvalue and the smallest eigenvalue. So here you have to know the largest eigenvalue of your Hessian and the smallest eigenvalue of your Hessian to get this rate. Now, for those of you who are numerical linear algebra people, you're probably saying, this is a least squares problem. Why don't you just run CG or something off of it? And you can't. The point about this algorithm, note, is that you get the same rate as CG in complexity. You still get that root kappa. And the other reason why this algorithm is popular is because it can be extended beyond just the least squares. So this is a very, very simple algorithm that can extend. It's easy to implement, and it can go beyond least squares. Okay. Just in case anyone is interested in this, where this algorithm actually came from is that CG was first. Okay. Then people were trying to extend it. So they were like, how do we extend it? You can't directly extend CG. So what they said is that, well, maybe if we fixed the parameters so you don't change your step size over time, you fix them as a constant and you look at the optimal polynomial for the least squares, you would get the momentum one. That's where it comes from. It's exactly that. Huh? But of course, there's a downside of this algorithm, which is that you need the smallest and largest eigenvalue. Okay, so I'm going to assume that. But again, all of these first order methods, you can always associate with some polynomial in this H. So there is a polynomial of H, and actually it'll involve Chebyshev polynomials of the first and second kind. Okay. So what did we see? So we saw that we have this property of these PKs, these polynomials, that we can relate each iterate of xk to a k degree polynomial. And these polynomials, of course, well, they're polynomials in H. They are just related to the eigenvalues of the Hessian. Right? So what is the idea is that provided you have B, your target and X naught are not aligned with your eigenvalues, eigenvectors of your Hessian, what you can show is that the loss at the iterative xk is actually just equal to, in some sense, the normalized trace of the polynomial in the H. There's some constants in here. It's not exactly the same polynomial, but it's the idea. Okay. So what is it saying is that this xk, this iterate, is just basically completely determined by the eigenvalues of the Hessian. Okay. Now, if you assume a little bit stronger, for instance, if you assume that B is from a generative model, so you take A times a signal x tilde plus some noise, and x tilde and this noise are isotropic and independent of your data matrix A, then you can also get an even clearer expression for the loss, which is that it's related to, again, this normalized trace of this polynomial in H, and it decays at like 1 over root n. So it concentrates as n gets large to just this trace quantity. Okay. Here, R and R tilde are the signal to noise ratios. So they represent the noise. But the main point of this is that you can do this for every first order method. It concentrates around this deterministic function, which just involves the eigenvalues. That's all you need to know. Predict. So what does this end up doing? Well, it turns out that the high dimensionality for these deterministic first order methods and the worst case complexity that we normally give are actually quite the same. Okay, means that we did pretty well by doing worst case complexity. That this 1 is root kappa, or sorry, 1 minus kappa here, which 1 over kappa, which is the rate of gradient descent, is roughly true in the average case. In the high dimensional, it's the same no matter what. Okay? So we did pretty well. So this is just to point this out. You can get finer analysis, but it's exactly the same. Okay. But in reality, when we're looking at machine learning problems, we don't actually do those deterministic first order methods. What we actually run is a stochastic algorithm. There are many, many reasons. The most reasonable one that people always talk about is from a computational perspective. Okay, it's cheaper to run a stochastic algorithm than it is to run the full matrix. Okay, so what is a stochastic algorithm? So here I'm going to do stochastic gradient descent with momentum. So here I have, again, the least squares problem. So I'm minimizing AX minus B. But here I can think of my loss as just a large finite sum of AIX minus BI. So AI is the row of your matrix. So my FI is just one sort of term in here. Okay. So what do people do is they say, okay, instead of moving in direction of negative the full gradient, they take an approximate of that gradient. How do they take an approximation of that gradient? What they do is they say, okay, I'm going to uniformly at random choose some indices I, okay? And I'm going to compute grad FIs of those guys, and that becomes my gradient. That becomes my full gradient, okay? So with that, you have to choose a batch size. So I'm going to let B be the batch, the number of indices I'm going to choose. I'm going to denote my batch fraction as the size of this batch divided by n. I'm just going to choose B number of these i's, and I'm going to compute those, and that becomes my estimate of my gradient. And everything else is the same. So I still have my momentum term, and I have my step size. Now, the issue with stochastic algorithms is, I don't know, hopefully some of you have implemented these. How the heck do you choose delta and gamma to make them run? And in practice, what people do is they just run a whole bunch of trials off of it. Okay, we have estimates, but they run a bunch of things. Okay, so choosing this delta and choosing this gamma and this batch are complicated. Okay, in practice. So what do we know about this? Well, let's just give a couple of ideas, although I won't talk about this. But when your batch size goes to 0, and you send the size to the number of samples to infinity, again, I'm keeping at the ratio n over d fixed, that the momentum, SGD with momentum, actually will have exactly the same dynamics as SGD. They're exact same path. We won't talk about this, but they're equal. Okay, so that's if you send your batch to 0, you recover SGD. So SGD is just where delta is 0. When the zeta becomes 1, well, you end up getting momentum, and so we know it's faster than gradient descent. So because we got a root kappa versus a kappa, right? So this kind of leads to this question of what happens in between, and do we gain anything from this high dimensions that we're tending to work in high dimensional spaces? Okay, so let's see what happens in high dimensions for a stochastic algorithm. So here I'm just doing stochastic gradient descent. Sorry, I'm going to choose my delta to be 0. I'm still going to look at a random matrix A and a random vector B. Okay, and I'm going to run batch stochastic gradient. And what you see in high dimensions is exactly what you saw for the gradient descent algorithm. That for large D, so for large models where you fix D over N to something, that the loss at the iterative SGD will actually converge to some function, deterministic function. Okay, this is despite the fact that I have randomness in A, randomness in B, and also randomness in the actual algorithm itself. I have concentration. So there's a lot of randomness going on here. Okay. Moreover, what is beautiful about this is you can actually analyze this function. So this is nice. You can actually analyze properties of it. You can get things about step sizes and batch sizes as a result of this completely deterministic function. Now, this function is also just determined, just like before, completely by the spectrum of the Hessian. That's all the information that you actually need. And so you see that here in this picture. So here I have iteration count. Here I have function values. What I've done is for each n, so n is 64, say I generate a matrix A, generate a B, run SGD 10 times, and I'm just plotting the spread of those runs. Okay, and then I'm increasing my n. Again, I'm fixing d over n to be some constant. I think here it's 1/2, remember? Okay, and you can see that the variance in the runs is going down. And in fact, it's just converging to this red line, and this red line you can predict. Yeah. We're going to talk, I'll tell you what it is in a second. I haven't told you what the function is or why I'm calling it a Volterra either. This is just to say that we're expecting that it actually concentrates and that we'll be able to write down the formula. So here's what it is. You predicted what's going to happen. Okay, so here we actually need to use high dimension. So here we actually are going to use the fact that A and B are large, okay, that we're working. So under some assumptions of high dimensionality on my matrix A, B, and my initialization, you can actually show that the loss function of the iterates of SGD or momentum, all of them, will concentrate around a deterministic function. What is this deterministic function? This deterministic function is a discrete convolution Volterra equation. Okay, so it looks something like psi, that's your function, which is equal to that, what you would have gotten if you ran full batch gradient descent plus momentum. So that's that polynomial thing, plus something else. And that something else is exactly the noise that SGD produces. And it turns out you can write down an exact formula for it, and it involves the loss again. Okay, so you get a Volterra equation from this. This W function, this kernel, if you will say, is an explicit function of the eigenvalues of H. If you actually, you can write it down for momentum, but if you actually look at SGD, it's a little bit easier. It has a nicer form. Again, you see you have these two terms, which corresponds to this green. This noise term is represented by this function here. So it's just, everything is just in terms of the eigenvalues of the matrix H. So what does this say is that you can actually say exactly how every eigenvalue of your Hessian affects the performance of SGD. Not just the largest and smallest, every eigenvalue. You have a formula for it, and you exactly know what the noise looks like. Okay. The other thing to know is that convolution Volterra equations are relatively easy to solve. Okay. Yeah. Yeah, actually, Elliot is going to explain some of it.
So at every moment in time, SGD makes a mistake.
Yeah.
The size of the noise is proportional to psi. W t minus k measures how much that piece of noise is as a result of the mean behavior.
Yeah, and we'll give an explicit thing in the next talk of showing that. Yeah. It's basically linear. Yeah. Yeah. I'm not assuming anything about sort of if it's tall and skinny or fat and wide. I just need that both N and D are large. So both the number of features and the number of samples are big. So it's rows and columns are both gigantic. It doesn't make sense, and they're proportional to each other in some way. So you're not in the setting where you have fixed fixed number, let's see, sorry, I always have to do my matrix multiplication. I guess fixed number of columns and the number of rows is extremely large. That's a different setting. I'm thinking of them both being sort of proportionally large to each other. It could be over or under, doesn't matter. It won't converge to won't go to 0, but it will converge to a constant value. It may not be 0. You may not, yes, but this is the loss function. So this is not xk minus x star. Right? This is the actual value of the loss. That will converge to something, just maybe not to 0, for instance. Right? It could converge to a fixed value. Yeah, it could bounce around. It will bounce around. Yeah. But the loss will converge, right? Yeah. Good question. Cool. Any other question before I continue? This is cool. Nice. It's actually quite nice. It's a Volterra equation. I always teach ODE, so I always include some sort of convolution Volterra equation every time I have to teach an ODE class now because it appears in work. So what actually are the assumptions? So maybe this is going into the details a little bit. They're going to be discussed more in detail with Elliot, but the basic idea is that you need some sort of proportionality of the model size D to N. Doesn't matter if this is 1/2 versus 2 over or under determined, just that they're on the same order and they're both large. D and N are large. I need some sort of that my empirical eigenvalue distribution of H is kind of converging to some compactly supported measure. I can't have things the eigenvalues getting too large. And then some mild assumptions on the largest and smallest eigenvalues of H. And then the other thing that I need is, this is where sort of this high dimensionality is going to be used, is you need some sort of delocalization of the eigenvectors of the Hessian H to make this work. In particular, one example is that you can use that your left orthogonally invariant is enough. So if I take an orthogonal matrix, I multiply it by my A, and law it has to be the same as A. But what you'll see is that this is too strong. You actually just need a delocalization, which Elliot will talk about. So examples which satisfy this are sample covariance matrices. Okay, where you have a covariance on the feature side, not on the sample side. So you have to have independent rows. Okay. And the other common one that you see is in machine learning is a random features. So this is where you take the product of two random matrices, and then you put a pointwise activation function on it, and you call that your A. This is used to model neural networks quite a bit, two-layer neural networks. Just for the moment, I'm going to assume I have a generative model. So my B is of the form A x tilde plus some noise. Okay. And this x tilde and this eta are independent of A. And then because I'm going to be working in high dimensions and I'm talking about convergence stuff, I need to be a little bit careful that I don't accidentally make the signal too powerful in the limit as n, or make the noise become the dominant feature. So what I've done is I've normalized everything so that my signal to noise ratio is constant across dimensions. So I'm not increasing the noise or increasing the signal accidentally by increasing dimensions. Okay. And this, again, is the full theorem, what you can actually prove. So what you can show is that if your step size is sufficiently small, so this is actually a strict convergence threshold. Okay, so if your step size is small, then you can show that the loss of the iterates of SGD converge with overwhelming probability to this deterministic function. And that function is a convolution Volterra, as I said before. Now, you're like, this is great, kind of, right? Like, what can you do with this, right? I mean, it's cool, right? It's actually quite a beautiful formula. You see how every eigenvalue affects the thing, but can you actually get any information from this? And the answer is yes. You can't actually start getting information. You can get information about rates and how to actually choose delta and step sizes and batch sizes. So what you see here is because of this extra noise, well, what you see here is that there's sort of a competition going on. So you have this decrease happening, but you see this function here depends on things like the step size. So once the step size gets too large or the delta gets too big, the momentum parameter, this noise starts to dominate. So you have a competition between the rate that you normally get from momentum plus the noise term. Okay. And so basically the idea is that for some of the gamma and delta, this noise term is going to actually slow you down. It's going to prevent you from reaching the same rate that you would have gone if you had just pure full gradient. And that's what you have in a picture here. So what you actually see is that you can find from a rate perspective that you have an actual max of 2 terms. The first term is what you would have gotten if you had of just pure full batch momentum. And the second is due to the noise. That's actually SGD, or that's actually what the noise is doing. And it's a max, a direct max. Okay. And so you can actually plot this because everything is deterministic at this point. You can plot what happens to the concentration, the convergence rate as a function of the learning and the delta, momentum parameter. So this picture right here for a fixed batch is just plotting what this lambda is, okay, for each gamma and each delta. And you see the max, the best thing happens here. On this thing here, should pay attention, is what happens with the noise. And this black represents this regime where this noise parameter doesn't even exist. It doesn't affect you at all. So and then this is actually in the last picture, the overall rate of convergence for the algorithm. So you would take the max of these things. So you get this sort of phase transition appearing. For some values of delta and gamma, you have the noise just doesn't even has no effect whatsoever. Okay. And you can do this for various batch fractions, which I'm plotting down below. And you can see where this red line is sort of the split where you start to see the second term, the noise start to affect versus the unnoise. And what happens over time is that this is the optimum that you would have gotten if you had it unnoise, and the noise starts to affect your convergence rate as you make your batch get larger. So this all relates down to condition numbers, and in the end, so what actually ends up happening is that it's an effect of you can relate this back to conditioning. So here what's going to play a role is actually the average condition number versus sort of the classic. The average is just the normalized trace, okay? And what you can see is you can actually choose the optimal parameters. So I didn't write this, but you can actually choose exactly what gamma and that delta is that nearly optimize your convergence rate. And they involve basically this kappa bar, this average condition number, and the actual full one. That's what you get. And I'm running out of time, so I'm going to do a little bit of it. And because the convergence rate involves these max of these two things, you can also start to talk about what is a good batch fraction that you should choose. And so what you see is a phase transition in the batch fraction, which is that if your batch fraction is larger than the ratio of the average over the square root of the classic condition number, you actually start to get square root behavior for your convergence, square root kappa convergence. If it's less than this, you actually end up exactly in SGD rates. So you actually have a dichotomy between these two. You can actually directly say that you'll end up having something which looks like SGD. And so you have a picture of this. So here's as I increase my batch fraction versus my convergence, you see that there's actually a saturation point. What this means is that you can't just add more and more data and expect to get faster and faster convergence. That's not how it works. You can add more and more data, and at some point, it doesn't actually improve your convergence rate. And this adding more data doesn't occur when your batch fraction is 1. It occurs somewhere in between. And so just to end, because I'm going to run out of time, you can also ask this question then, because there's this relationship between the SGD rate, which is this involving this average condition number versus the classic condition number, when is SGD better than momentum, full batch momentum? Well, it's when this ICR is less than 1, and you can actually plot what this is, this ICR, for various data sets. And what you see is that for most data sets that are actually used in practice, SGD is the better quantity. Okay, you want to run stochastic gradient descent. You don't actually want to run momentum. You want full batch if you can. Okay, and for many of these sort of simulated data sets, like where you assume a Gaussian, you're actually better off running gradient descent in some ways, full batch. So I'm going to end here because I'm running out of time, and I did run out of time. This is based off a bunch of works, and Elliot's going to talk more about the exact how you actually generate the SGD and where that Volterra comes from.